Hello, everybody. Let's take a look at chemistry today. Since we've been talking about density and melting point and all these chemical properties, it's important to talk about, well, what are all these substances? Basically, this is the basis of chemistry. And chemistry is inside us. It's in our DNA. It's in our drinks, like the caffeine molecule, for example. Look at how complex. It's got some hydrogen, some carbons, some oxygens. Even you have chemicals in the farts. What gives all the smells in the fart? So as you can see, that this is the one that causes the smell, the sulfide and the methane. But even gases that are coming out of our body are composed of multiple different atoms. It's the chemistry is also in what we eat. So these amazing French fries is full of fat, saturated fats, and unsaturated fatty acids. So all of those go into the chemistry. The molecules that we eat are all a part of what we eat. So and this is what explains, look how complex the molecule of fat is. It explains why it takes time to break it down and why do we feel so full after eating such a heavy meal. There's so many bonds to break between every carbon atom and every hydrogen atom. So now if we take a look at the notes in your notebook, I invite you to take your notes and open up to page 140. Yep. Nope, not 140. Sorry. 138. Yeah. So it's basically the particle theory or model are all matters made up of particles, everything. So all of the ones I've been talking about, we found the density, the melting point of these different substances. Well, I thought it would be important to talk about what are they? What are those substances? So they're all what we are made up of. It's all the matter that surrounds us. So you guys know this already. We have the solids, which hold their own shape, as you know. They're packed close together in crystals. And they have very little energy. And it can only vibrate. So think of an ice cube, which is solid water. And examples for those are gold, metals, any metal that we've been talking about. In the body now, we have feces and bones. So these are the solid substances. Now, if we take a look at liquids, they take up the shape of a container. So the volume is not defined like a solid. They're loosely packed. They have medium energy and they move a little bit slowly. And examples, you have water, of course, at room temperature. And in the body, all these liquids we talked about in the past, urine, bile, semen, blood, saliva, sweat, gastric juices. I mean, you can just write 3 examples from these that you know of. Now, if we move on to gases, they spread out to fill out the entire volume given. So they don't have a defined volume, no defined shape either. They take up the space in which they are placed in. And they move so much, they have so much energy. These particles move randomly. And examples of gases are helium, oxygen, carbon dioxide. There's hydrogen. So, you know, in the previous notes that we took, we did talk about the characteristic properties of gases. So these are examples right here that we talked about before. Now, if we take a look at atoms in specific in the famous periodic table, they are the smallest particles that make up the matter that exists. Think of the alphabet, right? We have 26 letters in an alphabet. So atoms are like each letter. We take a few letters together, they make up words. And you take a few words together and they make up sentences, then paragraphs, then entire books. So essentially atoms are like those letters. Out of just 26 letters, you can make millions of words in multiple languages. And same thing over here, we have 118 atoms, and there's always some new ones that are discovered. But with 118, you make millions of different compounds that surround us and that are in us as well. And they all have different sizes and shapes. Molecules now. So we go a little bit larger. It's like making the words with the atoms, with the letters. Molecules are groups of atoms now joined together by chemical reaction, which mean they can be divided chemically into separate atoms. The atoms can be the same or different. So like in these examples, can you guys tell me what this one is? CO2? That's carbon dioxide. And what about H2O? Water. And O2? And that's the simple molecule of oxygen. So that one, because you have two of the same, it is also called an element. Once you have two or more different atoms, now this is a compound. Again, this is a compound, and this is an element. So the water molecule, H2O, can be chemically divided into two hydrogens, and one oxygen atom. You see that? Like the Mickey Mouse. We have two hydrogens and one oxygen. The oxygen molecule now, two atoms of oxygen. And lastly, CO2, one carbon atom and two oxygens. So you look at the subscript that's on the right, and that's what gives you the amount of the atom. So here I have two oxygens. Carbon, nothing's written, but it's not zero. It's like a 1. Just like in algebra, you wouldn't write 1x. You don't need to write 1. So it's a bit like that. Same here, H2O, there's one oxygen and two hydrogens. These are just various other complex molecules that we talked about this year. The sugar molecule, glucose, if you remember. Urea, what is our urine made of? And here, Tylenol. This is the complex molecule of Tylenol. So really interesting how with just very few atoms, you can make millions of different compounds. Now, we have types of pure substances. And that's why I'm talking about pure substances now, because we just finished talking about density and different characteristics of metals, gases, and liquids. Well, all of the ones that we talked about, all these characteristics are all related to pure substances. A pure substance will react, will do what we talked about, will have a specific density. Okay, so a pure substance such as like water, for example, the compound of water, will have a boiling point of 100 degrees. Yes. And so it's really pure. Once you start mixing things together, then their characteristics change. It's no longer pure. Okay? So pure matter made up of only a single type. That's the thing that you have to remember. A single type of particle. So definitely not a mixture. So now if we look a little bit closer to elements, elements are one or more single type of atom. And it's the same. So nitrogen gas, for example, that we breathe is N2, is only one type, which is nitrogen. Ozone in the atmosphere, there is oxygen only, there's nothing else. Iron, only one atom of iron. You see how it's always one, and the way to tell is by one capital letter. So N, O, and F. Whereas in the water molecule, H2O, we have hydrogen and we have oxygen. These are two different atoms. And that's how you can tell apart between an element and a compound. So there's approximately 118, like I told you before, different elements that they have different shape and size. So depending on how many electrons and protons, they will vary in size. If we look closely at a molecule, it can be made up of different combinations of elements, and elements can also be called atoms. And all these elements can be found on the periodic table of the elements, which we have in our class. Each atom or element is given a different symbol, name, and number. So take a look at this box, and I encourage you to write it. on your notes, page 139, somewhere in the space at the bottom. So I'll give you a minute, write a box, draw a box. O for oxygen, write the name and the mass and the atomic number. So you should have a periodic table in your workbook, and you should have in the notes, in our notes as well. Find the page. Periodic table. I believe we have one, and if not, I'll make sure to print one for you. Yeah, it's actually on the last page, 152 in your notes. So if you take a look at the boxes, atomic number 8 and mass 15.9. So always the smallest number is the atomic number and the larger number is the mass. Each atom or element is organized according to their common properties. So we place them all. It's not a random placing. They are placed based on whether they react a lot or not. If I look at, for example, the first column where hydrogen is, you have lithium, sodium, potassium, all of these. When they are placed there because they all have the same properties. They react highly in the air. They have to be stored in oil. There are 25 elements essential to life, and 4 of them, carbon, oxygen, hydrogen, and nitrogen, make up 96% of matter on Earth. Now, the next part is the compounds. So we looked at elements that are made up of the same types of atoms. Now, if you look at compounds, they are particles that consist of 2 or more different elements or atoms and can be broken down into its constituent elements. So you can tell, right? You have all kinds of different atoms in here. Unlike O2, N2, F2, it's always the same one atom. Whereas here you have multiple different atoms. All right, I invite you to do this exercise. Which of the following molecules are considered to be a compound? Yes. NaSO4, CO2, H2O. Good job. All the others, look, it's a one capital letter, one capital letter, one capital letter. We have to add another letter next to it, a minuscule, just because otherwise we would have multiple C's. There are so many atoms on the periodic table that start with the letter C. And so we must have a second one to differentiate between them, between every atom. And these are all like, they are used, sometimes they're used from Latin words as well, from Greeks, from different countries. We use an abbreviation depending on when they were chosen, when they were discovered, by who, but mostly is Latin. So in all of these over here, we have capital letter N, capital letter S, O, and that's how you can tell you have different atoms, which means we have compounds. Counting how many atoms are in an element or compound. Look at the small number, like I said, after each capital letter. If there isn't any number, it is automatically a 1. So carbon, 1 atom. Bromine, 1. Iodine, 2 iodine atoms. H2O, 2 hydrogens, 1 oxygen. Carbon, 1 atom and 2 oxygen atoms. How many atoms are there in each of the molecules?